So section 8 is about ropes and pulleys. So,
What the heck?
yeah. So consider the box being pulled by a rope. With problems like these, where we're pulling with a rope, or if we have a pulley in a little bit, the mass of the rope is significantly smaller than the mass of the object that we're pulling on. So we make an approximation that the mass of the rope is actually equal to 0. Because relative to the mass of the thing that we're pulling, it is basically 0, because it contributes almost nothing. So in general, we're going to have a massless string or rope transmitting a force and tension undiminished from one end to the other. We will lose nothing in the process. The tension in the rope will equal the magnitude of the force pulling on the end of the rope, and the tension and force are an action-reaction pair. So those three things are things that we're going to be dealing with in this section. So in the picture, we have the box. We have the tension in the rope pulling on the box, the normal force up and the weight down, of course. In the rope, we have the force of the box on the rope pulling backwards, and we have the force pulling forward, and they are the action-reaction pair. So, the conceptual example here, we're pulling on the rope. So we have in the figure, this shows the student pulling horizontally with a 100 Newton force on a rope that is attached to a wall. Then we have two students in a tug of war pulling opposite directions, each with a 100 Newton force. Is the tension in the second rope larger than, smaller than, or the same as that in the first?
You know, he's probably going to throw a curveball and say they're both the same, but I think it's B.
I think it's the same.
The answer is, yeah, it's the same. So in figure B, pulling one way with 100 newtons, pulling the other way with 100 newtons, the tension in the rope is 100 newtons. In figure A, we only have one person pulling with 100 newtons this way, but the wall would be pulling back with the same action-reaction pair, 100 newtons. So the answer is that they are the same. So remember, action-reaction pair is very important. Okay, now we're getting to pulleys. So the ideal pulley, as you worked with in the lab, has it's going to allow us to change the direction in which the tension force is acting, but not its magnitude. So the ideal pulley here is going to be considered massless and frictionless. And that's what we're going to be dealing with in this section when we work with problems. So basically, the pulley is just changing the direction that the force is being applied, and nothing more. It does not reduce tension. It does not introduce friction. It just changes the direction that we're applying the force for an ideal pulley. So the string or rope or whatever it is passes over the pulley. The static friction in the rope and pulley system causes the pulley to turn. That's fine. The string and pulley are both massless here. There is no friction in the pulley's axle, therefore we're not losing anything in that little system right there. And then tension is unchanged in the string as it passes over the pulley. So we don't lose anything as we change the direction of the applied force. So these conditions represent what we call an ideal pulley, and that's what we're using in this section, and generally in physics when we're working with pulleys. So, working with ropes and pulleys. If the force on the end of the rope is pulling, then the tension in the rope equals the magnitude of the pulling force. So we're going to have a tension in the rope. So tension in the rope might be here, and that will equal so this tension right here equals the magnitude of the pulling force, and the magnitude of the pulling force in this picture would be like the mg of the box B there. The two objects are connected by a rope, so the tension is the same at both ends, just like we were talking about with everything being horizontal. And then the rope passes over the pulley. The tension in the rope is unaffected because it's an ideal pulley. So that's the situation with the pulley, and this picture should look pretty familiar. Okay, so now placing a leg in traction. So this is an example of how we would use a pulley in a situation where it's actually very useful. So for somebody who seriously fractures their leg, the leg may need to have a constant stretching force applied to keep the contracting leg muscles from forcing the broken bones together too much, too hard. So we want to keep the tension off of those muscles so that the bones have a chance to come back together in a sort of a more gentle way. So the traction, if you've ever heard of somebody being put in traction, this is one way that that traction can be done. So it's an arrangement of a rope, a weight, and pulleys, as we can see in this figure right here. So the person is put on a beam, a bed, or something like that, and then we have sort of an attachment up here, like on the ceiling or something, and then the rope comes down, attaches to the stretcher or bed or whatever they're on, or to this joint that they have right here, and then comes back and aligns here with some weight. And what happens is that creates a force pulling backwards on the leg to keep, hopefully, the muscles from contracting and pulling that joint or the bones, keep those bones from pulling back too hard, and actually allowing them to align correctly so that they can stitch back together the way that they're supposed to. So let me get rid of all of these markings now, and let's finish reading the problem. So the rope must make the same angle theta on both sides of the pulley so that the net force of the rope and the pulley are pulled horizontally, as we see in the picture here. So this force has to be directly horizontal to the right, but theta can be adjusted. So we can adjust this angle theta to control the amount of traction that we're going to get. So the amount of force then that's being applied to the leg. The doctor has specified 50 newtons of traction for this patient with a 4.2 kilogram hanging mass. So we have this hanging mass over here. We know exactly how much that mass is. What is the proper angle theta then? What angle theta do we need here in order to put the correct amount of traction, which was specified 50 newtons, on this patient? That's the problem that we have to solve. So what we're going to do is we're going to draw a free body diagram for this picture, and I'm just going to put that directly under for me to save space. So the free body diagram will be basically at this pulley right here. So I have my pulley, and then I'm going to have a tension up here. I can call that T1. I'm going to have a tension down towards the weight here. Call that T2. And then I'm going to have, didn't draw that horizontally, but it's meant to be horizontal. And this is the force that's being applied. So we have the force that's being applied here, and this is the leg on the pulley. So the leg is pulling back on that pulley. In the free body diagram, we also have the pulley on the leg. That's the action-reaction pair. So this is the leg on the pulley here, pulling backwards on that pulley to give us this angle that's being presented in the picture.
So how come in your free body diagram you don't have to draw the force pulley on the leg going?
It's an action-reaction pair.
So it doesn't matter.
Okay, so I'm also going to draw the axes on here a little bit. A lot of times I don't bother with it, but I'm going to put those on here just real faint. So right here, here's my y-axis, and here is my x-axis, just so that we kind of have an idea what the directions are. And I need that because on this picture, I have an angle theta sitting in here, okay? So here's my x-axis, here's my angle theta. Now also I know that this would create a right triangle here, and this would create a right triangle here, okay? So my angle theta is this guy, and also the same thing is true here, angle theta.
Wait, if it creates a right triangle, then theta would be,
Theta is the same in both.
so it'd be 45 degrees.
The right triangle is here.
Never mind.
Okay. So now, as with all problems, we need to break these into components. So we're going to have a T1x and a T1y, T2x and a T2y. So let's do that. What would T1x be?
The x-axis.
Good question. The same as T2x?
But I want to break them into components. So T1x would be what once it's broken into components? We're going to use cosine. Yeah, so it would be T1x is T1 cosine theta. And if you're not sure on that, just go ahead and set up the full-on proportion and then solve for T1x, and you'll see it's T1 cosine theta. So then T2x would be what? T2 cosine theta, for the same reason. Oops, cosine. Okay? Now, what do we know about those two forces?
Those two are equal.
They're equal to each other. So I can say T1x equals T2x. Okay? What else do I know about this whole situation here?
Theta is equal to each other.
Is the leg moving?
No.
The leg is not moving.
That force is 0.
So F net equals 0. So back on my free body diagram, I can write that. F net equals 0. All right. So at this point, I'm going to go ahead and do my sum of the forces. So I'm going to say, let me change colors here so I'm not confused. Sum of the forces in the x direction equals, what do I have?
Negative F.
You got
Okay, yes. Negative F, the leg on the pulley, sure. What else do I have? T1x and T2x.
Put those two equal. So you would go with 1 and equal.
I'm going to write down exactly what I have right now before I start substituting stuff in. So I have T1x plus T2x, and I have a negative F, and that was leg on pulley. Okay, and that would normally equal mass times acceleration in the x direction, but we have a net force of 0, so this equals 0. Now, what do I know? I know that T1x is the same as T2x, right?
How come you're adding them together?
Yeah, that's just about to ask.
Why am I adding them together?
Because if you move one to the other side, then it would be equal to negative 2x.
They're both in the same direction. They're both in the positive direction. T1x is in the positive direction. T2x is in the positive direction. So they are both positive.
Yeah. I
So
was just
they're
thinking,
added.
Like if you were to move it to another side, then it wouldn't show that they're equal.
But I wouldn't want to move it to the other side. I'm just setting up my forces, the sum of the forces in the x direction. And T1x is in the positive direction, T2x is in the positive direction, so I have T1x plus T2x. Okay? All right, so now I know that T1x and T2x are the same thing. Also, I know that T1x is T1 cosine theta. Okay?
Okay.
All right. So
So if they're equal, you can only use one. You can make it to where you only use one variable.
I can make it to where I only have T1x or I can only have T2x, right?
Yeah.
And because they're both the same thing, really what I have here is two of them. So it's 2 T1x. All right, does that make sense?
Yeah.
All right, so I have 2 T1x. Yes?
Yep.
Okay. Now, if that's the case,
That means you only have one variable.
She moved there 'cause she was coughing on it.
then the other thing is, shh, we also know that the tension that's here is equal to the tension that's here.
So T1 equals T2.
So T1 is actually T2. They're both the same thing because as we roll over the pulley, we don't change anything. Okay? So T1 is actually T2. And so saying T1X is irrelevant to saying T2X. They're both the same thing. So I actually don't even need to change T1 and T2. It's just T. So what I really have here is simply two tensions cosine theta.
Wouldn't it still be in the x direction though?
Do I need it in the x direction?
No.
I don't.
And then that equals your,
So then I can say equals F leg on pulley. Okay, what is it that I'm looking for?
The angle.
I'm looking for the angle, so I can continue to solve for theta here. So I'm going to divide by 2t, and then take the inverse cosine of both sides. So I'll have theta equals the F leg on pulley divided by 2t, but I'm taking the inverse cosine of that whole thing. And now I can plug in all my numbers. So I have theta equals inverse cosine F leg on pulley. What is it? It needs to be 50 newtons. And we have 2 times the tension. Well, what's the tension?
4.2.
It's not 4.2, but it's going to be 4.2 kilograms times 9.8 meters per second squared. Okay, so we make sure our calculator is in degrees, and we're going to get our answer. Theta equals what? 52.5993. Okay, well, let's look at our significant figures. What is our answer going to actually be?
this one, 50.
So what is it? Yeah, we only have 50 newtons, so the answer actually should be 50. You know what, would not argue with you if you said 53 degrees. Even though it seems like the answer should be 50, 53 seems a little bit better here for me. All right, let's see about this one. We have a 200 kilogram set is used in a play, and it's stored in a loft above the stage. So the rope holding the set passes up and over a pulley and then is tied backstage. The director tells the 100 kilogram stagehand to lower the set. When he unties the rope, the set falls and the unfortunate man is hoisted into the loft. What is the stagehand's acceleration?
Oh,
I was gonna say at first it was curious to know why we had another stagehand's weight, but that makes sense.
Okay, yeah. Do you understand what's happening here?
He's literally getting lifted.
It's a 200 kilogram set, and we have a 100 kilogram stagehand asked to lower the set. That don't work, right? So what do we do? Yeah, don't ask him to do it. Draw a picture, okay. Draw a free body diagram, okay.
I want to draw a picture.
Draw a picture then. I'm gonna go to the free body diagram.
yeah, me too.
Oh, come
I'm
on.
not an artist.
You guys are no fun.
Draw the picture. Who cares what everybody else is doing? I'm going to the free body diagram. So we're going to have the free body diagram for the stage. or the set. So we have the weight down, the weight of the set, and then it's being held up by a rope. So we're going to have tension in the set. Okay?
I'm pretty sure the weight has a greater magnitude.
Now we're also going to have a free body diagram for this person here.
So is this gonna be while they're in the air or while they're on the ground?
Does it matter?
Yeah,
Yeah.
because if they're on the ground, then we have normal force, but if they're in the air, we don't.
But we have a weight down and we have a tension up. So the weight of, now, I can't really use stagehand for S, so
P for person.
P for person. Okay, we can do that. And then the tension of the person. Does that make sense? What do we know about the tensions?
They're equal.
They're equal. So I actually do not need to write tension of the stagehand, or tension of the set, and tension of the person. It is just T.
That didn't answer the question. But now they just pointed it out.
All right, so now in this first free body diagram that I have here on the left, what is the F net?
It's mass times acceleration.
Mm,
Or it's, whatever it is, mass.
is there an F net, or is it zero?
It's not zero, the first net.
In the first one,
In the one on the left?
Oh, and that one?
that's zero. That's what I said.
No, because it's going down.
Hopefully,
So it's having an acceleration.
So it has an acceleration, which way?
Downward.
So what's the F net?
Down.
Down. Okay, so what is the F net in the one on the right?
Up.
Up. Okay, so in this figure, the rope extends upward and then connects somewhere along the way up on a pulley. All right, so now what do we need to do?
Well, let's do some of the forces in the y direction.
Some of the forces in the y direction is a good idea. What else do we need to realize? F net down, F net up. What is going to be true about these two things?
The accelerations are going to be equal.
The accelerations are the same. The acceleration of the set equals the acceleration of the person, except for one thing.
They're in opposite directions.
They're in opposite directions, that's right. So we can say the acceleration of the set will be what?
Negative.
Negative, sure. Because it's going down, and the acceleration of the person is positive because it's going up. So we'll keep that in mind as we go. All right, so we should probably do a sum of the forces set up for both. So let's do a sum of the forces in the y direction for the set. Sum of the forces for the set in the y direction. What do we got?
So you got tension minus weight
Tension
equal mg.
minus weight equals M
A.
A
Y.
set.
We don't have to, we don't have to focus on the y direction because there's no movement in the x direction, right?
Right, just in the y direction. So MAS, but what do we know about AS?
It's equal to AP, negative AP.
AS is negative.
Yeah,
So in a little bit, we're going to have to fix that, okay?
okay.
So some of the forces for the person in the y direction equals
Weight. It'd still be tension minus weight, wouldn't it?
tension minus weight
Equals MAP.
All right, and we said that acceleration will be positive because this person's going up.
Yes.
Okay, now acceleration for the set is same magnitude as acceleration for the person. So the A itself, does it need the subscript? No, it doesn't. But the sign needs to be fixed, okay? So I can rewrite these equations and say T minus W equals negative MA. And on the other one, I can say T minus W. These W's need to have a subscript on them, though. That's my fault. WS and WP. WP here, WS here, equals MA. And that one's positive. Okay.
Two things are equal. Not gonna mind if you do that.
Now, what are we looking for?
Acceleration.
We're looking for acceleration. In these two equations, we have tension, we don't know. Weight is mg. Do we know the weight or the mass of the stage or the set?
Yes.
Okay, so we do know the weight there.
We do not know never mind.
You can solve one of them for A.
And I should be using the subscript here also. M is what?
Stage.
Okay, MS, MP. Okay, sorry. Little sloppy with my notations. Okay, so we know everything except for tension and acceleration there. What about some of the forces for the person? Do we know the tension in the rope?
We can, because it's gonna be the mass.
We don't know it, right? Right now, we don't know it. Do we know the weight of the person?
Yes.
We know the mass, right? Okay, so we could calculate that. We know the mass of the person. Do we know the acceleration? No, that's what we're looking for, right? Okay, so there's two things we don't know, and there's two variables in both equations. So we can solve one equation for something and substitute it into the other. The question is, which variable do we want to solve for to substitute it into the other?
Wait.
Acceleration.
What are we looking for? We're looking for acceleration, right? So we would want to solve for the other thing that we don't know, because when we substitute it into the other equation, we're going to be left with the thing that we do want to find. So I want to solve for tension. So that I substitute it into the equation, and tension is gone, and I'm left with acceleration, which is what I want to find. It reduces the amount of work that I have to do. So I'm going to solve for tension in this equation. Tension equals weight of the set minus mass of the set times the acceleration. So now I can solve, I've solved for tension. I can substitute that into the other equation. So the tension now in the other equation is the weight of the set minus the mass of the set times the acceleration. And then I have minus the weight of the person equals the mass of the person times the acceleration.
So now you just divide by the mass of the person.
Well, I have an acceleration still over on the left-hand side and acceleration on the right-hand side. So what I want to do is I want to get everything in terms of mass, gravity, and acceleration so that I can solve for acceleration, okay?
Acceleration, which then would eliminate acceleration.
So this is the mass of the set, gravity, minus the mass of the set, acceleration, minus the mass of the person, gravity, equals the mass of the person, acceleration. Now I want all accelerations on one side. So I'm actually going to add the second term to the other side. So I have mass of the set minus mass of the person, mass of the set, gravity, minus mass of the person, gravity, equals, and now I added the mass of the set to both sides. So I have the mass of the set, acceleration, plus mass of the person, that's an M, mass of the person, acceleration.
Can you divide them?
Now, on both sides, I have a GCF. I have on the left side a GCF of gravity. So I'm going to pull out gravity, mass of the set minus mass of the person. On the right-hand side, I have a GCF of acceleration. So I pull out acceleration, and I'm left with mass of the set plus mass of the person. And now I'm trying to solve for acceleration. So I'm going to divide both sides by the mass of the set plus the mass of the person. And I'm left with acceleration equals, and it will be gravity times, on top, the mass of the set minus the mass of the person divided by the mass of the set plus the mass of the person. Okay? Now, this is exciting because we have basically a formula here
But can you,
that tells us exactly what it is. It's gravity times the mass of the set minus the mass of the person divided by the mass of the set plus the mass of the person. So even if we didn't have any numbers, we would have an answer right here that is actually very elegant. But we do have numbers, so we can plug in these numbers. We have acceleration equals 9.8 meters per second squared times, what is the mass of the set? 200 kilograms. What is the mass of the person? 100 kilograms. And then divided by 200 kilograms again, plus 100 kilograms. And we can do this in the parentheses in our heads. We see that the kilograms are going to divide out. So we have 100 on top over 300 on the bottom. So we have 1/3 times 9.8 meters per second squared. We can do that little bit in our heads, and now we have an easy calculation. 1/3 of basically 10 is around 3.3. Do the calculation. What do we get? 3.3. Meters per second squared. So we have our next problem. We have bank robbers pushed a 1,000-kilogram safe to the second-story floor-to-ceiling window. They plan to break the window, then lower the safe 3.0 meters to their truck. Not being too clever, they stack the 500 kilograms of furniture, tie a rope between the safe and the furniture, and place the rope over a pulley. They then push the safe out the window. What's the safe's speed when it hits the truck? By the way, the coefficient of kinetic friction between the furniture and the floor is 0.50. What do we do? Well, let's draw a picture of the situation. So we have the floor of the building and then the side of the building. And then down on the ground here, we have the truck. So amazing truck. This is the type of truck that criminals definitely would be driving. And then we have the pulley up here, furniture, rope, down, safe. Okay, safe, furniture. What do we know is going on here?
that safe is gonna crush the truck.
Probably. But this is 1942 Ford,
So it's the trucks that ain't gonna be able
back when they were built well. So down, we're going to have an acceleration here for sure. The mass of the safe is what? 1,000 kilograms. Okay, and then we also have the mass of the furniture,
It's half of that.
500 kilograms. All right, we have
Would've been smarter.
an acceleration this way. What do we know about those two accelerations?
gonna be equal.
They're going to be the same. Okay, and we have a coefficient of friction here. Mu sub k is 0.50. We also have an initial height from here down to the truck, y sub I was 3 meters.
Oh, 0 meters.
So then what's y sub f going to be?
0.
0 meters.
That's really not that far.
9 feet.
9 feet is pretty good. Okay, what else do we know? Would we be able to calculate velocity here?
Yeah.
So what's v sub I?
Unless they pushed it that far.
Our velocity initially is 0.
0 meters per second.
Velocity 5.
We're being asked to find the safe speed. So we're looking for v sub f equals, I don't know. All right, so we have basically a delta y. Are we going to be able to calculate the acceleration? Yes, we are, because we're going to have forces to deal with. So we're going to have an acceleration. We have a delta y. We're looking for velocity. There's a formula that deals with that. Do you know what the formula is? V sub f, v sub I, and acceleration, and the delta y.
Yeah.
It is v sub f squared
Yeah.
equals v sub I squared plus 2a, well, it's not x this time, it's delta y this time. Okay, so we're looking for that equation. We need the acceleration, and basically that's it, right? Okay, so calculate the acceleration now. So we're going to set up a free body diagram.
So you're going to have a force in the x and the y direction.
Free body diagram for the furniture has a weight down, weight of the furniture. We'll have a normal force up. We're going to have a kinetic friction force, F sub K. And we're going to have what going to the right?
Thank you.
We have a tension in the rope. The tension, you could call it sub F, but the tension in the rope is the tension in the rope no matter what, so we just call it T. Now, for the safe,
Weight down.
we have weight down,
Tension out.
weight in the safe down, and we have tension up. Oops, tension up.
And on top.
Okay, it goes over the pulley. We don't lose anything, so T is the same as T.
We're gonna have to calculate in the future the pulleys friction
No, we use ideal pulleys
all the time.
all the time.
I like that idea.
Okay, now what?
Some of the forces.
Some of the forces in the
X and y.
X and Y, because we have both directions going on here. So some of the forces in the X direction would be what?
Negative FK plus T.
Yep, okay, so we have the tension minus the friction kinetic. And do we have a net force? We didn't talk about that. For the free body diagram for the furniture, F net is
Right.
to the right. And for the free body diagram for the safe, F net is down. Okay, good. So some of the forces in the X direction, T minus F sub K equals MA. Is it X or is it just MA?
It's going to be
MA.
It's all the same, acceleration. Okay.
What you need to put at A.
It doesn't matter because it's all the same acceleration.
You have to label the furniture, the mass of the furniture.
MF, thank you, yes. Okay, and some of the forces in the Y direction.
You're going to have normal force minus weight for the furniture.
So we have tension up minus weight of the safe down equals
MA.
mass of the safe acceleration.
So how come you don't have to include some of the forces in the y direction for the furniture? You only did it in the x direction.
sum of the forces for the safe.
No, for the furniture in the X direction, or for in the Y direction.
I haven't gotten there yet.
Oh, okay.
Some of the forces for the some of the forces for the furniture in the X direction, some of the forces for the furniture in the Y direction. What do we have?
And minus two.
Okay, normal up minus weight of the furniture down equals
0.
0. We don't have a net force in the up direction, so it's just 0. Okay. Now what do we do?
So see what we need on.
We're looking for what, speed, not acceleration?
We are looking for speed, but we need to calculate acceleration first,
So we can use that formula at the top, yeah.
so that we can use the formula at the top, yeah. Okay, so the sum of the forces in the Y direction for the furniture, normal equals the weight of the furniture. The weight of the furniture will be the mass of the furniture times gravity. The sum of the forces in the X direction for the furniture includes F sub K. What do we know about F sub K?
It is 0.05.
F sub K is mu sub Kn, right?
Yeah.
Okay. F sub K is mu sub K,
Times mass of the furniture times.
and mu sub N is M sub F G. So we have mu sub K, M sub F G. Okay. So now back to the sum of the forces in the X direction. We have tension minus F sub K, which is now mu sub K, mass of the furniture times gravity, equals mass of the furniture times our acceleration. What happens?
Divided by furniture.
I can't do that because I have this tension force and I don't have mass in all three.
So you're going to add it to the other side, right? So then solve for tension.
I can solve for tension. So I have tension equals, I can write mass of the furniture acceleration plus mu sub K mass of the furniture G. Now what?
Solve for T in a different equation.
Well, G
And then
equals
substitute.
Okay.
the weight of the safe plus mass of the safe.
Okay, so I come back up here and I can solve for T also. T equals the weight of the safe, but the weight of the safe is mass of the safe times gravity plus the mass of the safe times our acceleration. So now what?
Now plug that into your T, the bottom equation, right?
So you want to set all those equal to each other? Yeah, basically set them equal to each other. So I can write equals right here. So I'm just taking the T on the left side and saying equals M sub S G plus M sub S A. What is it we're looking for?
Acceleration.
Acceleration. So I'm going to do exactly what I did on the previous problem and move all the acceleration terms onto one side. So I'm going to subtract the M sub F A from both sides and subtract the M sub S G from both sides. So now I have mu sub K, M sub F G minus M sub S G equals M sub S A, and I subtracted the mass of the furniture A, so minus M sub F A. Okay, now my next move,
Take out,
I can take out the G,
take out the A.
and I can take out the A on the other side. When I took out the a on the other side, I would have the m sub s minus m sub f. I'll have to divide. And that's what I get. When I took out the g, I have the mu sub k, the m sub f, and the minus m sub s left over. So that's what I have. So now I can plug in all those numbers because I know every single one of those things. I'm going to need a calculator probably. Maybe not. I have 9.8 meters per second squared times mu sub k was 0.50 times the mass of the furniture was 500 kilograms minus the mass of the safe was 1,000, right? Divided by the mass of the safe again, 1,000 kilograms, minus the mass of the furniture, 500 kilograms. So that would be 500 on the bottom. Half of 500 is 250 minus, so negative 750 divided by 500. What is that? 3 halves?
Yeah.
So negative 3 halves times 9.8. 4.9 times 3. Is it around 15? No.
Good.
Around 5? Negative 5? It's around half anyway.
What is the answer?
Oh, I got a plus sign. This is a plus sign. Sorry. This is a plus sign.
So 750 over 1,500, which is 1/2. Which would be
Where do you get the 750? Oh, because of that.
Yeah, this one's a plus sign here. So it should be a half, basically a half of 9.8.
which is 400.
So 4.9. So the acceleration is 4.9 meters per second squared, and it's negative. Because of the minus 1,000 on top. So we'll finish this one off, and the section, we've got like 5 minutes left here, and we'll finish that.